I'm Kate Donahue, and I'm going to be presenting joint work with Alexandra Chouldechova and Krishnaram Kenthapadi on human algorithm collaboration, achieving complementarity and avoiding unfairness. So for this task, let's think about a motivating example. Imagine that this is a prediction task, and say that it's something like a doctor is looking at a patient's medical record and making some prediction as to whether or not the patient has a disease. So the status quo is just this: the doctor is making some prediction based on her own expertise. And a lot of machine learning research is focused on building a machine learning model that can do this same task with lower error. But a lot of times the end result will not be just replacing the doctor with this algorithm, but will rather be the doctor using the algorithm in this situation here. And one question you might really care about is, will this resulting system be better, right? Will this overall system be better than the status quo? And obviously the word sort of, what do you mean by better? There are a lot of things that could be better here. The most obvious thing is sort of lower error. And here the term complementarity is been used to mean a system that has lower error than either the unaided human or the algorithm. And this diagram on the right just gives a very simple example of this, where the unaided human has loss 0.75, the unaided algorithm has loss 0.5, and when this human is using the algorithm, in this case, it is average loss 0.45. And so this is achieving complementarity. But obviously this isn't the only sort of, just like reducing loss overall isn't the only thing we might care about. We might also care about fairness. And in our paper, we think of at least two notions of fairness. The first is fairness of benefit, which is basically meaning, do all people or do all sort of instances that could be predicted upon by this algorithm see their error reduced when the algorithm is added? So basically, is it the case that for every person who's being predicted upon with the human using the algorithm, every one of them sees their error decrease as compared to, say, using the human only alone? And ideally, sort of achieving fairness of benefit would be something that would be very nice for this overall system. The other notion we consider is loss disparity. And this is just the gap in loss between different parts of the input. And this is a more standard notion of fairness. You can just think of like any sort of notion or gap in error rates between different parts of the input space. And here you might care about that if they represent sort of certain sensitive groups. If certain people have higher or lower error rates than others, we might naturally think this is unfair. And ideally for this sort of combined system, we would want the combined system to at least not exacerbate unfairness, right? We'd like that this at least doesn't make the combined loss higher. Ideally, it would be nice if it sort of compressed the losses and made things sort of fairer in this way. So in our paper, what we do is we give a formal and tractable model for just modeling these human algorithm collaborative systems. Then we give concrete conditions for when we can and can't achieve complementarity. And finally, we end up by discussing fairness, so saying when fairness of benefit and loss disparity can be achieved. And we also discuss this in connection with complementarity and showing that in some cases there's tension there. For more information, listen to the full talk or read the paper or come talk to me during the conference. Thanks.